Good evening. I see you folks having snacks and beverages. We'll start in a few seconds. So start taking your seats. But first of all, I'd like to thank you, all of you who came today. Um, we'll have three speakers, and it will be presented by Paulus, Saulius, and Giedrius. Um, The first talk will be about logging. The second one about data pipelines with Golang. And the third one about assembler in Go. Uh, Lots of exciting things to be heard today. After the talks, as usual, we'll have some prizes, giveaways. So keep your ears tight and listen carefully to presentations. We'll have a quiz at the end of a show. And as always, we'll have a networking event. For me personally, networking is where the magic happens. I can watch a lot of YouTube with technical talks, but events like these are meeting people. Okay, thank you for your attention. And Polo?
Hello everyone, my name is Paulius and I today will present you a practical guide to sLogging. So without further ado, let's check the topics. First of all, we will start with the very basics. We will do with levels, then we will pass with the groups, then some random stuff like valuer, and we will end with handler and some other random stuff. So sLog was added in Go 1.21. This is 575 days ago. And random fact, it's a palindrome, which means if you read that in reverse, you get the same number. Okay, let's start with very, very basics. What sLog offers? sLog offers 4 different levels. So debug, info, warning, and error. And if we would try to use that out of the box, we would get these 3 beautiful messages. So why that? Because levels are integers, and by default, integer defaults to audience 0. Okay, so in order to set another level, we need to use another function like setLog level. We do that with, we pass the debug level, do the out of the box stuff, and we get our beautiful 4 messages. Okay, now we know how to set level, but just let's go to some practical news. You know, you have an application and you want to extract use that level and pass it, for example, via environment variables. And to, say, make a little less verbose, passing error logger as a result. So in order to do that, we just define a variable of a slog level type, and we use default unmarshaled text method to pass environment variable value. And we set a slogger level to our log level, and as exactly out of the box, we get only error. So, but how about other levels? Trace, notice, warning, general, those fancy Google levels, or your own dragon level. So let's create a Goku level. In this case, we will define that Goku level as a level -6. And we use a function that a little bit different of the default. It takes context, log level, message, and arguments. We set the level, and we try to log that out of the box plus our own. and we get these 5 messages. Do you notice something different? Does anyone notice something different? No? Okay. Debug -2, super tracing Cygen. It's not a level of Goku, yes? So why does this happen? This happens because levels have a concrete type and you cannot intervene with it. And how it calculates, it just takes your integer level and compares with the default values and basically either pluses or minuses the below level of info or other. So how do we pass a custom level in our case? In order to do that, we can use the same approach that we used before, and just we would need to pass a debug -2. Also, we could pass debug -5, -8, -11, -9000. It will all work because they are lower than the debug. So basically what you get, a debug and minus whatever number. So it's not a really practical approach to do that because you would need to math if you have, for example, trace or super trace levels. So in order to approach that and to solve this problem, we could define our custom level and do that unmarshal text method, what we had before, and check for Goku case. If the string Goku is passed, we use our level Goku. If not, we default to a level unmarshal. And with that, we can pass Goku level, not the debug minus something. And in the end, we would get the same output that they get before. Okay, so next one, a dynamic level. This one is interesting. How dynamic level goes? Dynamic level lets you to change the level on a runtime. What that means, you can change it to info, debug, or whatever while the application is running. So in order to do that, we will jump a little bit ahead and create a handler. We will pass a standard error output and a handler options in which we pass our dynamic level, which we created as a global variable in this case. One good example how can we do that in our real world application is, for example, create a handler, imagine like API./admin, change level where query parameter legal equals level 1, 2, 3, 4, 5 to some level Goku, debug info, or over 9000. And we have, what we have slider. This, I'm sorry, this was supposed to be Go slides, so a little bit interaction in here. So just imagine the slider is moving, and when you set a Goku level, you would get a lot of information, but if you change that to warning in a running application, you will see that the warnings and errors start to appear and debug and info would disappear. But if we go to the errors, the same approach, warning disappears and only level error appears, and dynamic level we will see that it's error, and the same can be done with lag off. So we basically can turn it off. Why is it helpful? So if we have usually application, we set log level in the environment variables. In order to change that, we would need to restart our deployment. Please raise a hand who has done that, who has restarted the deployment in order to change log level. Lots of you, thank you. So if you had a lot of applications, a fleet, restarting application may cause some downtimes or some unexpected behavior from the consumer or customer side. So this approach lets us to debug information while application is running, and while it's running, we do not need to restart it. so it does not cause disruption in our clusters or somewhere where the application is running. Okay, so a little bit of parameters. Replacer. Remember that we had a debug -2 at our Goku level. How can we fix that? A replacer gives us such ability. It's a function that accepts groups and a sLog attribute and returns a sLog attribute. What we can do with that, we can check if the logging level is of our Goku level, and if it is, we can substitute with the string value Goku. We, again, create a new text handler, pass a standard error, pass a logger options, again, level and replacer, do our logging level Goku super tracing Saiyajin, and we get this beautiful message like level Goku. So Goku approves us. So to summarize levels, sadly a concrete type is used and we need a custom logic to apply our workarounds in order to have our beautiful message to pass it or see it in the logs. And dynamic level gives a huge flexibility in order to increase or decrease logging without causing disruptions in production. Another random fact. Did you know that slogging is an actual word? It means to work hard over a long period, especially doing that work in a difficult or boring slides. I hope you're slogging well right now. So, okay, groups. There are two ways to add groups. We have function group, which takes a group key and key value arguments, and with a group name. So what you can do with both of them. The first one, a sLog group, lets you to group key value arguments into some groups where it makes sense. For example, you have a middleware which logs request and response. So both request and response have headers. And in this example, we can group them in request and response groups. So basically you have headers, both keys are the same, but the group key, request or response difference. Headers also could be different or could be the same. Why is this helpful? Because imagine if you are using more structured logging like JSON, and if you use the same key, some libraries could drop it, some logging frameworks could drop in, some collectors could drop in, or could be duplicated. So this helps us separate in a nice way. Also, you do not need to write response underscore headers or response headers uppercase, something like that. Another one, groups with group context. So basically, here's an example. The difference between group and groups is that with group applies group key to all values. Previously, we applied group to particular ones. In here, we apply to all of them. So imagine that we have a user getter and a legacy user getter was identical to user getter, but just uses legacy. What we do we create a new logger, we pass it to the user getter and use a legacy getter with the group arguments, and we just range and call get function for them. What we get this message, and we see that the message is identical, but the only difference is the group key. So user 1 is G, and legacy user 1, 2, 3. Okay, next thing is valuer. Valuer is something that you can attach to your custom type, which helps you to log custom way of that attribute. Imagine that you have an API which accepts API token or some kind of password. You could attach a sLogger value to it, a method to it, and change the way it logs. So in this case, let's imagine we have a token, which is super secure token, and we try to log it. In this, with the token would have that log value method, it would be outputted like this. We see redacted and MD hash of that. Where it helps to debug in very corner situations when you are dealing with secrets and you do not want to leak that secrets in your logging collector, but you still need to know if that is correct secret was passed. So corner case, but it's very useful in that case. Okay, before jumping to handlers, I would like to a little bit talk about sLog architecture. So sLog architecture is defined from three things. It's basically a logger, which is a user-facing API, which we call debug, info, error, those functions. We have a record. This is information that is bundled and passed to the backend, and the backend is called a handler when we can do anything with that information that we want. So what is a handler? A handler is anything that implements these four methods. It's like enable, handle, with attributes and with groups. And how sLog handles it, it is first calls enabled to check if either the logger is enabled or not. This is the first optimization. And the second one is it calls with attributes to do some pre-formatting. So basically, you are able to do something with the attributes in a way you want before outputting it. So what handlers do we have? A text handler, we already seen that. A JSON handler, which basically puts JSON instead of text, and the brand new discard handler. So basically, it does nothing and discards it. So use it in tests or something. Also, it accepts handler options. Two of them we already discussed. So leveler and replacer. Add source basically adds the log line where it was outputted. Okay, so how about custom handlers? Custom handlers allows us to create our own handler. For example, YAML. Why I call it in the quotes, because it's not entirely YAML, it's just like indented and does not support full values, but it doesn't matter. So we see our time, level, key value groups, and down below we have a checksum of MD for this log level. So let's go a bit deeper. So how this handler is implemented? You create an options. It's optional, of course. You create a group or attributes where you store a group and its attributes. You use a mutex and you have your writer. So mutex is used to protect the writer of simultaneous calls. So, and we create a new logger with the basic simple information predefined like info level and mutex initialized. So inside the handle, first thing first, we create a buffer to which we will write and which will be outputted. First, one of the optimization which is recommended is to create predefined byte slice. Why? Because if you do not define its size, it by appending you would increase and increase and increase, and that slows it down. Another thing that we check the time also. This is based on the documentation and how they recommend it. So we ignore the 0 time if it's not passed. Then we add the level. Then we check for our log line, which was printed. And we append some messages and so on. Next, we deal with attributes. So what we have is just like pre-format and prepare our groups and attributes. And then when it was pre-formatted and ordered in the way we want, we just pre-append that in our buffer. And basically, we have added a custom logic. So here's a perfect place where you can add your custom logic. In here, we just check checksum. For example, you are working with payments or some sensitive information, and you must ensure that your logs are not tampered. Here's a way to do it. Another way we could add, for example, a channel in here which passes some audit log it to some other handler, or we get, I don't know, pass it to the third-party servers by calling something. It's up to imagination. So, and lastly, we just write it out. So yeah, what can we do with our logging? Sometimes, usually oftentimes, we use context, and sometimes context in our logging is missing. So you probably have a lot of functions seen in this, like this. In this case, the first one is just adds request ID to the context, basically request output, and the other one just outputs that value as a string, as a sLog attribute. So who has done similar things? No one, actually. One person uses context. Wow. Okay, tough public. Okay, so what can we do? We create this, and we create a simple middleware that uses that, and that's context. So basically, we have our handler, which info context. We use a different method info context. There are 4 methods for this, 5 if we include 6 actually if we include log and log attributes. So info, debug, error, and warning both have context. Basically the same argument, just they take the context. Also, we go to the downstream. Downstream simply do stuff. You see below. It also just logs. And we have a handler which takes context extractors. It's a function that takes context and gives us sLog attributes. And inside out the handler, where we see that when we saw that where we extract mdsum in this case, sorry. Okay, somewhere. We extract it instead of mdsum, and what we get this beautiful info message where we just simply log handling request and passing downstream and pass context, but suddenly a magical red request ID appears. So now if we have a huge volume amounts of requests, they have a correlation ID, like request ID, in which we can track the same request in the logs. It very helps to debug. For example, if you have 17, 20 something calls and different messages, you have one ID, just find it all and you know the log flow. So, okay, what else can we do? Let's have a little bit imaginations. Groups. Can we apply custom logger to groups? Yes, we can. Let's create a custom logger which accepts groups as a string array. We have the same with group, which basically checks if the group is on our name and returns default handler with a group name, or just discards the logger. So if we use new groups handler and just pass legacy user getter from the previous slides, we would get this message. Only legacy user getter is printed, but both legacy user and user getter is used in the get function. So only legacy user is getter. And if we add user getter to this list, we would get both messages. So basically you have an ability like a Spring Boot where you have logging levels, some random package path, and then level actually, and you are able to control specific parts of your logging imagination. So why does this helpful? Where it helps? When you have a huge application, for example, okay, maybe simple application is also works in this case. You have a handler, you have your business domain, and you have a database for persistence level. You know that handler works, you know that business domain works, but there are some problems with the persistence layer. You could use groups, for example, log only persistence layer in this case, and that's lower your output message. Why it's valuable? If you have an application with a 5 user, it doesn't make sense. If you have an application with 50 million users, it makes sense because the output information is very huge and you increasing your noise, it doesn't help for debugging. Okay, we are ending this. So last thing before I end, optimizations. It's generally useful to use infolog, but if you are getting in the stressful point when your CPU is used by logging, it is possible to use an alternative log with attributes, log attributes, which basically do the same, but instead of arguments, any, accepts a sLog attribute. And how does it help? It's already pre-formatted. In some way, my personal opinion is more clear. And when the handler appears, you already have log attributes, so you don't need to parse them or do stuff with them. So yeah, general tips. Try to log once. It reduces noise. If possible, use context. Use magic to provide some correlation ID. It will help you to track information. Avoid creating hard cardinality logs. For example, this is a bad example where the message would constantly change based on status. So if we have status 500, that's one message. If we have status 505, that would be another message. If we would want to search that, you would have to, pipe those all numbers. Logs are intended for humans, so don't make metrics out of them. Use metrics for that. One of the password was incorrect or authentication does not succeeded. It does not give you any information, and in order to do that, you just simply log metric. It will make your life easier. When you're implementing custom handlers, check the official documentation. There's a lot of tips how not to shoot yourself in the leg. And if you want to have your custom output like YAML or something fancy and not like encrypted logger, if you have the need for that, you can have a test-your handler, but you need to write your own parser for that. But the sLog gives you a basic starter kit for this. For example, you can pass your handler to a sLog test, does handler, and it would check if your parser accepts your log. So yeah, that's it from my side. Any questions? None. Okay.
Thank you for the presentation. So there are I wanted to know more about your personal experience. There are okay, it's hard to talk when you hear yourself. So there are a ton of logging libraries out there, like hundreds, and even Go has logging, now sLog. So my question is, what are the chances that in 5 years we will have sLog v2, for example? Does it miss any huge functionality, and how does it work for you personally?
I think, Ego, my personal opinion, I'm more of a logger architectural way because in my opinion, you just need 2 ways, info and error, and everything that goes higher is just additional info. There are no levels. So basically, you just control, like a slider we see, you just control the output. But talking about sLog, it covers majority of the functionality that someone needs. So if we start a new package, most likely new gophers would go for sLog. Old-timers could go for sLog also because it removes dependencies. So if you have, for example, some, I don't know, ISO standard which enforces you to control third-party dependencies, you just simply avoid, because it doesn't matter in the end if you use third-party or this, if just the info log message needs to be. So it will gain traction because it has coverage, but it needs momentum because we have Zerolog and Zap taking the, it's a train and it stops slowly because it's just heavy and have a heavy community underlying. So this is my personal opinion. Anyone else?
So I was wondering, how many log levels are you actually using in production?
2.
But you basically gave a talk that suggests that we should use a lot of them.
No, I just explained that they have 4 + 2 functions and you are able to use that.
Okay.
So this is basic talks for basic gophers, and I imagine that you have never used the logging package before. So I personally avoid warning levels because it causes a lot of discussions between engineers. Do you need to react that? Do you need it? Do you ignore it? So it's confusion. Always do error or info. It's straightforward. Understand. Anyone else? No? 3, 2, 1. So thank you for slogging with me.
So thank you, Paulius. Now it's Saulius. Saulius will talk about how to build a 1 gigabyte per second pipeline with Go. It should be pretty exciting. Welcome.
Testing, testing. These are not my slides. All right. Hello, everyone. My name is Saulius. I'm a founding / principal engineer at CastAI. And today I'm going to talk about how we built a 1 gigabyte per second pipeline, data ingestion pipeline. And this talk, in all honesty, is kind of an experiment, whether it's possible to talk about architecture in 30 minutes about a thing that needs a lot of context. So I hope it's going to be a successful experiment. All right, introduction. So what am I going to talk about here? So CastAI is a SaaS platform that needs to ingest a lot of data from thousands of Kubernetes clusters. So we are talking about cluster snapshot ingestion, right? So I'm going to talk a little bit about the context, what scale challenges we had, and how we approached it. Basically, what Go libraries, techniques, etc. were crucial in implementing this pipeline. All right, a little bit of marketing. So what's CastAI? It's a Kubernetes automation platform. First of all, we have more modules, but this is, for this particular talk, this is the most important. And we have 3 major modules, so autoscaling, reporting, and security. And autoscaling includes node, workload autoscaling. So basically, you create a pod, it doesn't fit, we create a node, it fits. You no longer need the node, we delete the node. Easy. For reporting, we have cluster resource utilization, resource cost, potential savings, reports, etc. And everything is real time. We also have a security module, which analyzes your cluster, what's running in it, how you set it up, etc. And issue detection, prioritization, and remediation is also, everything is real time. And all of these need data from your cluster. And we have one single SaaS platform. So how do we, okay, first of all, let's talk about the scale challenges and like what SLAs were given to us. So first of all, 15 seconds. This is the interval at which all the services expect new data. And 15 seconds is because well, this is actually an arbitrary number, but this it's basically how we saw that the cluster changes meaningfully in 15 seconds, right? Maybe new pods appeared, not just some annotation changed, right? Also, services need historical data, so at least 1 day old data in 15-second intervals. And services need both snapshots, like what is the full state of the cluster, as well as deltas, so what changed between 2 points. And just to show you what we're dealing with, this is a screenshot of one of our customer clusters. I tried to like obfuscate who the customer is, but yeah, so this cluster is actually in a quiet period. It had 2,600 nodes, 23,000 pods. And if you look below, you can see that it sometimes scales up to about 300,000 CPUs. So it's a massive cluster. Obviously, not all of the clusters are that big, but we have dozens of such huge clusters. And yeah. All right, so I hope you're bearing with me. So let's dive in. So first of all, we have a Kubernetes agent. So obviously we need data from Kubernetes, and we need to get it somehow, therefore Kubernetes agent. So we deploy it in customer Kubernetes clusters. And when we started developing it, the main tenet was that it is supposed to be as, well, for the lack of a better word, as dumb as possible. Because it should only move data from the customer cluster to the mothership. We call our platform the mothership. And you, of course, can read the code. It's open source at our casti/Kubernetes agent GitHub at your own time. All right, so this is a high-level diagram. Bear with me. So whenever you do anything in Kubernetes, create, update, delete, or whatever, it has to pass through the Kubernetes API server. And fortunately, there is a way to get CDC, change data capture, from Kubernetes. And this is what our Kubernetes agent is using. So every 15 seconds, all the changes are pushed to the mothership. Okay, so what do we use there? So first of all, we use the informers package from the Kubernetes Go client. And the main idea behind it is to just provide CDC capabilities for Kubernetes. Almost all Kubernetes controllers use this. And basically what it does is just lists a certain resource. For example, if you're interested in Kubernetes pods, you can create a Kubernetes pod informer, which lists all the pods. And after the request is over, you get a resource version back with which you can start then watching for changes. So whenever any pod is changed, you will get a new version of that pod delivered to you. And all of the informers, so we have dozens of them, right? So pods, nodes, volumes, ingresses, you name it. And they all end up in a work queue. So this work queue library is actually not coupled to Kubernetes. It is in Kubernetes client package, but it's a pretty generic implementation of a work queue. So you can actually use it in your own projects. It's pretty useful. So it acts as a sink for many informers. And then there is another process, sorry, not a process, but a Go routine, which picks data from the work queue and caches that data with debouncing, right? So basically, some clusters are very chatty, and nodes are sometimes updated many times during those 15 seconds. So we ignore the changes and just retain the latest version of the node. Even though CastAI is an AI product platform, and some of those changes would be very interesting to us, but due to the load, we just decided to ignore those extra changes. And then every 15 seconds, all that data is sent to the mothership. We also have implemented a way for the agent to monitor its own memory usage. Basically, it looks for memory pressure, and if there is, then it tries to relieve it by sending the data sooner. And this is these are the request metrics that come from Kubernetes agents. So the top line is the max observed request size. So the requests are, well, they're larger than in your, I don't know, run-down-the-mill web server, but they're not that big, right? We have like peaks of about 128 megabytes, and these are for the largest clusters. So, and these only contain the changes, right? And the average of a request is quite small. It's about 512 kilobytes. Yeah, so, and these are all gzipped. So gzip JSON. So if you unzip it, you get about 10 times more data. All right, what happens when the request ends up in the mothership? So first of all, the general principles, tenets, or whatever you want to call it, how we approached it. So if there is any logic at all, it has to be in the mothership, because we believe that owned environments are easier to change, observe, and fix, rather than hostile environments such as customer clusters. Also, we are dealing with 99.95% uptimes SLA, because we are essentially managing customers' infrastructure. So everything has to be super reliable. And we're also very conscious of infrastructure costs, because we are in cost efficiency savings business, right? So we have to dog food. How does it go? Preach? Do what you preach. All right, and yeah, because like 1 gigabyte per second, it adds up to 1 terabyte every 17 minutes. This is just raw gzip data. So if you know clouds, you know that the bill for networking is insane. So what we ended up doing, so the API endpoint itself, so it's literally the simplest possible mux. It's just a function handle, response writer, and request. Most services in CastAI are using gRPC with a gRPC gateway that acts as a translation layer from REST to gRPC. But machine-to-machine communication is using gRPC. So we initially started with the same thing. You know, you have a hammer, so don't update. I heard from colleagues that you basically then end up with a dead computer. All right, so we tried to bend gRPC to our needs, but it was just impossible. So if you ever looked at gRPC server implementation, you will see that whenever it receives a request, it first loads all the request body bytes into a buffer and then reads it again to deserialize into a Go struct. And yeah, that doesn't work when you're reading gigabytes, right? So what we ended up was with just like we scrapped all the gRPC and exposed a simple HTTP endpoint which allows us to pipe all the bytes and do logic at the same time as we are reading the request. So we also do absolutely no deserialization to Go, and we utilize the JSON parser library, which essentially allows us to trigger logic as we are reading the JSON. So yeah, and all bytes are piped as from request to uploading to the storage, so nothing is duplicated. This doesn't work anymore. Thank you. All right, and data processing. So what do we do when we receive it to that simplest possible API endpoint? So we have this process called folding, fold. So this is actually, I think, a pretty wide topic and could be a talk in of itself. But to put it shortly, folding is a process where we apply changes to the latest snapshot to end up with the current snapshot, if that makes sense. So once we fold it, so that it has a lot of interesting optimizations. Like, for example, we are always working with bytes, and we are actually indexing the latest snapshot to know which byte slice means which pod it is, because we need to, some changes are deleting pods, some are adding pods, and some are changing pods. So we need to understand where each pod lives and efficiently replace it or remove it. Once we fold, we upload the change snapshot, but we first upload it to historical storage. And then we upload all the deltas. The deltas are kind of implemented automatically due to the way the agent is working. So we don't really need to do anything there. And then we trigger server-side copy to the latest storage, which overrides the snapshot. And then we publish a new message about data. So let's talk a little bit about the storage itself. So initially, we started with storing the snapshot in Postgres. That did not go well. So we hit table limits, but not the ones you might think. So the snapshot table was actually not full, but there, I don't want to expand too much on it, but Postgres works in, stores data in 8 kilobyte pages, but a snapshot might be 100 megabytes, right? So how does it achieve that? So there is a technique called toast, and this toast basically splits your 100 megabytes into 8 kilobytes chunks, and with a relationship between them. And that table is in a completely different database. So we were actually not even aware that we were hitting the limit before we hit it. And there is a vacuum process running underneath that is supposed to clean it up. But because we were creating such a large load, the vacuum was not able to keep up, and we hit the table limits. A table limit in Postgres is 32 terabytes. So we had downtime, of course. We also tried applying various good techniques, but not maybe for our use case. So like load balancing, routing, and caching. This worked pretty well. So the group cache library was pretty good. Basically, we were just trying to route agent requests to the service that had the latest snapshot cached, so that we could save up on network traffic and time to process the request, to deserialize it, etc. But it was kind of too complex. But the thing that pushed us over the edge to use something else was actually that it was super expensive. Because the way the group cache works is that you create a cluster of services, participants, and whenever one participant gets something into the cache, that cache is then distributed to all the participants. So imagine what happens when you have a multi-availability zone cluster with, let's say, 30 participants, and 1 gigabyte per second gets sent everywhere. You get thousands and thousands of dollars per month. So we scrapped everything, went back to the drawing board, and we ended up using just a simple storage service, right? So S3. And if you think about it, it literally covers everything we had before. I don't know why we didn't start initially with it. We were overthinking probably. But yeah, so no need for load balancing. There's one endpoint. It's scalable because it's Google scale. You don't need to do anything there, and it's also super cheap compared to what we had before. Because traffic between your VPC and S3 is actually free. You literally don't pay anything for it. You only pay for operations. So the more times you upload, the more you will pay. But if your uploads are like 1 gigabyte large, you will not pay for that 1 gigabyte. So it's much, much cheaper. Okay, that's it. Thank you. So this is our metric of our load of that endpoint. Yeah. Any questions? I guess not. Thank you for your time.
Okay, so it's time for our last talk, which will be presented by Giedrius. Could we change the slides, please? Thank you, Saulius.
It works. Hello, everyone. I'm Giedrius, and I'll be talking to you today about Go assembler. Hopefully, you will find this interesting and learn a thing or two. And I will also be presenting some fun facts about Go development and how it all works under the hood. So every good slide, of course, starts with a who am I slide. So I'm a observability engineer at Vinted in the observability infra team. We have a huge observability stack where we store traces, logs, metrics, all kinds of signals, and provide the platform for our users, our internal developers. Personally, have been working on observability stuff the past 10 plus years, and I've been writing Go for even longer than that. And I also short blog on giedrius.blog, so if these topics interest you, feel free to jump over. So a bit of theory to start, to be on the same page. So what the hell is an assembler? Most people know about it, but I'll just reiterate it so that we would all know what it is. So assembler, simply put, is a program that accepts assembly language as the input and outputs machine code. Of course, Go, at some point during the compilation, translates the Go code into assembly and to the assembly language, and then assembler converts that into the machine code. So it looks something like this. You just have a bunch of instructions that have mnemonic names. That's a hard word to pronounce. Mnemonic means that the instruction names follow the functionality. So for example, move moves value from one place to another, add adds one value to another, jumps to some label. First fun fact, Go uses a Plan 9 style assembler. So for those who don't know, Plan 9 is kind of this niche distributed operating system that came out of Bell Labs in, I think, 90s. It was initially written by Rob Pike, Ken Thompson, and other people. So you might know Rob Pike as also one of the initial authors of Go. And Ken Thompson famously worked a lot on the C programming language. He, of course, it's my opinion, wrote this legendary book called The C Programming Language in the 70s. And then he also wrote a book, The Go Programming Language, in the same style and manner. So I would recommend you to pick those up if you want to know more about Go and do the exercises. So what's the relation between, of course, besides that, the authors are shared. So Plan 9 has this mascot called Glenda, and we have our own Go Gopher, and actually they were drawn by the same person, René French. So not only there are similarities, like because the authors are the same, the mascots are also drawn by the same person. And what's worth stressing here in this slide is that these three instructions are called scalar instructions. They work with one data point at a time, and that assembler is still an abstraction. So it's not it translates the assembly language into machine code, but it's not the same, like assembly language is not machine code. And what we are interested in is CMD, single instruction, multiple data. So these are extensions that various CPU manufacturers have. And CMD extensions are specialized instructions that allow the programmer to work on multiple data points with one instruction. These things are also called vectorized instructions or vectorized registers. And they are called vectors because they are extended. So for example, there's a register called XMM1, which can contain 128 bits of data, whereas a regular register might fit only 32 bits of data. So with CMD extensions, you can, for example, fit four 32-bit integers into one vector, and then add those two vectors together. And with CMD extensions, that will you will only need to use one instruction instead of 4 add instructions. So with that you can do more with the same or fewer CPU cycles. Just to name a few names, how they're called: SSC, AVX, and Neon. These are probably the most popular extensions. SSC stands for Streaming CMD Extensions, AVX Advanced Vector Extensions, and Neon is like some name that ARM came up for their processors. So yeah, by using these instructions, you can squeeze more performance out of your computer. And that's what we want, write faster programs and save the environment. So yeah, I'll just reiterate why you should care. Of course, it's my own personal opinion, but CPUs nowadays are not getting much faster. It seems like the focus is more on adding more CPU cores to computers instead of making them faster. So by using these CMD instructions through the Go assembler, you can squeeze more performance out of your programs. And writing Go assembler code is the only way to access them. Disclaimer, Go assembler and CMD extensions are like a huge topic by itself. really not possible to fit everything into 30 minutes. I was researching this topic and I found out that there's like a few months ago, a white paper came out where some author just wrote down the history of CMD extensions, and there are like 10 plus of them, and each of them have their own like nitty-gritty details that you need to be aware of. So it's not possible for me to cover everything, and if you want to know more, feel free to check out these links. Another disclaimer is that you don't need to go and jump and like optimize all of your code. I would always recommend you to profile your programs to find out which code paths use the most CPU time and focus your optimizations efforts on those parts. Another thing that is worth mentioning is that it might not be so easy to use CMD extensions because you might need to update your data structures. So how did I even get started? Like, why do I even care about Go assembler? So I work a lot on monitoring systems, and I sometimes contribute, but and we run Prometheus internally. And what Prometheus does is it's a monitoring time series database, and inside of that database, it's a very common operation where, let's say, in Prometheus, you have this concept of label matchers. So if a user sends a query where they want to know where label A is equal to B, and let's say foo is equal to bar, then what Prometheus does is that it retrieves two sorted lists of integers and calculates the intersection of them. And this is being done during every query execution. So I started looking into how to make this faster because it's such a common operation and it takes a lot of time. If you have, like, for example, 10 lists of integers with 10 million elements. I stumbled upon this white paper, CMD compression and the intersection of sorted integers, and I just screenshotted one of the tables from that white paper where they showed that. So just to comment a bit on these results, there are like many ways of calculating that intersection, and in this white paper, in this table, they are looking at the SVS method, set versus set. And as you can see that the CMD version is more than 4 times faster than the scalar one. So I was like, wow, I need this. Prometheus needs this. So I looked more and more into that. In the past, I worked with some C and C++ code. And so I just wanted to show you how it looks like in other languages. In C, on the left-hand side, you can see what is called inline assembly. So this C extension allows you to write some assembler code directly in the C code. So what this does is simple. It just adds the constant 1 to the source and moves it into destination. The result is 2. And on the right-hand side, you can see another variant of how other languages do it. This time it's C++. And in this picture, you can see what is called CPU intrinsics. So CPU intrinsics allow the programmer to use those extended registers as variable types. And the compiler does all the magic for you. And you can also call CMD functions, and they look like just regular functions. The programmer doesn't need to do anything. I was like, wow, this is really good. Let's see how Go does it. Well, apparently Go is a simple programming language. I don't know if it's really simple, but yeah. Every month or 2, or maybe half a year, someone reappears on the Go issue tracker and they propose over and over again, adding some kind of like exposing CMD functionality or the assembler in a nicer way to the Go programmer. And so far, all of those proposals have been denied because, yeah, they want to keep the language simple. It's their choice, but it's still possible to write assembler, to call assembler code from Go. Yeah, so what to do? So another interesting thing, Go compiler cheats a little bit. If you call certain functions from the Go code, the compiler can convert them and does convert them, if possible, to the actual corresponding CPU instructions. So for example, if you want to calculate one's count in some integer, the Go compiler will just replace it with pop count instruction, which does everything. And you don't, and the end result looks like that you are just calling that instruction instead of calling like that one's count function. So the Go compiler thinks that it's smarter than the programmer and does some things behind the programmer's back. Let's put it that way. So the second thing is how to call assembler functions from Go. You might have not known this, but in Go, you can define functions without a body. You don't need to actually define the body in the Go code. This is a quote directly from the Go specification. Here, some flush iCache function is just defined with no body. So the body must be defined somewhere else. Well, how to include that assembler code into your Go program? Go compiler also has got you covered. So Go, you probably also don't know this, but Go automatically includes .c, .h, .s files into your compilation. You don't need to do anything. So you just need to write assembler code in the C and the S files. Okay, so coming back to my example, this is the interface that I am working with inside of the Prometheus code base. All lists have this interface where you have to call next continuously in a loop and then call at to retrieve the current value. So if next returns false, there are no more values. And if next returns true, you just call at to get that value. So yeah, I read that white paper, implemented the CMD version, and benchmarked it, and the numbers sucked. So I wondered, like, what happened? And apparently, if you write your functions, if you write the function body in the assembler, the Go compiler doesn't inline your function calls. So modern programming is based on creating small functions that do one thing well. But if your CMD function, let's say, or any kind of assembler function, if it doesn't get inlined, that means if you are calling some function continuously, you're paying a huge price for calling that function. And the naive scalar version gets inlined. So the loop is much less expensive compared to the CMD version. So what you have to do if you're writing assembler in a Go program is that your assembler function will need to do much more work in one function call to accommodate for the fact that the Go compiler won't inline the assembler function. Yeah, so my recommendation, always benchmark and check your own code. You might think that CMD makes it magically fast, but that might not always be the case. So this, I don't know, just a book recommendation. I worked on it myself, so I can kind of vouch on its quality. So how functions look like in assembler. This is a simple function called foo. It just returns the constant 42. Yeah, so we should always remember that this is still an abstraction. So So for example, ret is a virtual place where you can put, where you should put return values. And ret, for example, there's no, like you can, the Go assembler converts it to what, like ret means return to the caller, and the Go assembler does, like replaces it with actual instructions. But we can just write ret, and it will return 42 to the caller. So do we always need to write assembler code by hand? No, because life would suck that way. There's actually this great library, Avo, that I would recommend you to use if you will ever write assembler code in Go. So what it does is that it allows you to use regular functions and create a generator that will generate assembler code from Go code. So that you can see that this is much nicer compared to writing everything yourself. And as a bonus, you can integrate it with Go generate, and you also get nice error messages. So for example, it checks like for various common small mistakes that you might do. So it prevents some of the foot guns. So a few recommendations for the end. I would recommend you, if you're debugging assembler code, to disable inlining and all optimizations on all packages through this flag. This will make the executable more, this will make it a nicer experience with debuggers because no code will be optimized out. You can also use the site godbolt.org, where you can explore what's the assembler output of various compilers, and Go is part of them. So you can see that the same foo is generated. Of course, the output is a bit different. Func data is an optional thing. It just specifies some metadata for the Go garbage collector. Yeah, and it just colors everything in a nice way. Another thing I tried is using a debugger. So I would recommend you to use GDB or Delve directly for debugging. I haven't tried JetBrains, but with VS Code, for example, I was not able to access the contents of the registers. But with GDB or Delve, it's very easy to do. Almost the last slide. Just wanted to note another like small thing. If you have a variable that is allocated on the heap and you want to call some method on it, how does it look in the assembler? So apparently the address of foo, in this case, of the variable of that variable is passed as an extra parameter to that function. So just the first parameter becomes the address of that variable. Yeah, so bright future ahead. I would certainly say that assembler in Go is not a first-class citizen. Even if that's the case, there are like lots of great libraries that exploit CMD instructions. There are lots of cryptographic, not crypto as in money, but cryptographic libraries that use those CMD extensions that are much faster than the scalar ones. There are lots of great compression libraries like Klauspost S2, for example, that provide faster versions of the snappy compression and so on. And let's hope for the best in the future, and maybe Go 2.0 will make it easier to use the assembler interleaved with high-level code, and it won't be so painful. Thank you. Any questions? Yeah, just .blog.
I have a question. Doesn't Go itself optimize optimize your code during compile time and make it faster to run on hardware? And why doing it yourself in assembler is better in your opinion?
So Go, yes, it does optimize the code. It performs various optimizations. But they try to maintain, they target common hardware. Like, for example, they will not, okay, I'll explain it in a bit different way. It does optimizations, but doesn't do a lot of them. Like, for example, Rust auto-vectorizes loops. So Rust uses LLVM as an example under the hood, and they automatically convert some loops to use the CMD extensions. But Go doesn't have that because you only have range and the regular loop. So Go tries to be simple. So optimizations, they optimize a lot, but they don't use the CMD extensions because they want those binaries that are produced by the compiler to be portable. So I don't know, like it's their choice. They don't do as many optimizations. I think it's in part because the Go compiler, I think it was written just for the Go project itself. And there are things like the LLVM that are used as a base in a lot of other languages. And they do, for example, lots of more optimizations. So maybe, I don't know, like in a few years, the situation will be different because we have in the recent version, there has been a lot of improvements on loops in Go. So you can write, I forgot how they're called, but you can write your own iterators in Go nowadays. Like in the previous version, 1.2.3 or 1.2.4, I don't remember. So like my personal opinion is that we are working, the Go compiler is working towards using those CMD extensions out of the box through the compiler, but not yet. Like it's a
Okay,
complex question.
Follow-up question. When you're writing assembly code yourself, should you aware on what hardware you run your program?
Yes, the code, the assembler code is much less portable. So you're writing the assembler code for some particular platform. And if you want to support more platforms, for example, ARM x86, you will need to write assembler code for each platform. So it's more work.
Anyone else?
First part of the question, do you think you could use that in production, like that library that you showed, or is it just for playing?
I still haven't finished my work. It's more of the work started as out of personal curiosity. Just I work a lot in the Prometheus Thanatos code base, and like I just want to. It's out of curiosity, like how to make it faster, because some queries are slow, and I just started looking at why they are slow.
And okay, so when it will be ready for production, how do you think, like, how do you find functions that would benefit from that, right? Maybe I can use it for my 1 gigabyte per second pipeline.
Maybe. I don't know, just reading white papers. Google. Because so, like there are some common operations, like for example, a Prometheus, okay, like this is a cool metrics database that does lots of things, but at the very base layer, it does like this fundamental intersection thing. And then you work from that, like Google how to make it faster, because like I didn't show it here, but there are many ways to calculate the intersection. Some of them are faster, some of them are slower, and you just start from there and dig into it more.
And how do you then like test that code? Because you probably need, or do you just keep the same unit tests as you would test Go code? What's the approach?
Yeah, I mean, you can just run the same unit tests, and if they still pass, like verification of programs it's a complex, very complex topic. But yeah, that's my approach. Run the same tests, and if they pass, then it's probably correct.
Okay. So thank you, Gedris. Yeah, applause. Now we'll go to last part, or almost the last. Networking will be the last. We'll have some traditional giveaway. They will be giving few books and some cold weapon. It's a 1,000 pages book about Go. So who'll win it? I'll be subscribing for updates once you read it. Okay, so take out your phones. And join with QR code. Okay, see people joining. If someone needs more time, let me know, and we'll be moving to the next page in 5, 4, 3, 2, 1. I counted almost 50 of us. It's 30 registered. Let's go. Okay, what is a palindrome? Okay, I see a few people thinking what it is. Paulius was very nice to share that. Jokubas, oh no, Gedris, Edvinus, and almost everyone answered correctly. So keep in mind, it's not only about the correct answer, but it's about speed as well. So don't think too long. Okay, next question. What does sLogging mean? Curious to see who will be the next leader. Okay, everyone answered. Gedris maintains the lead. But I'm not sure if Gedris doesn't have conflicts of interest because he prepared the last 3 questions. Where Jerry will decide who to eliminate from the podium. Okay, the last from Paulius. How many times Son Goku has been shown during the slides? A lot. Definitely more than 10, no? Vilnius goes to the first place. It's over 9,000. I would have clicked one as well. Okay, so now it's from a second presentation. What endpoint does CDC in Kubernetes API server or any other well-known database? Okay. Vilnius maintains, users gets to the second place. It was a watch endpoint. What storage service is used for cluster snapshots? Yeah, Saulius mentioned it. Actually, I'm even confused of answer. Everyone is so close. It's S3. S3 on GCP, very confusing. What was the two main reasons for getting rid of local cluster snapshot hashing? Two main reasons. DP isn't the third place. Too expensive and complex. Last question from Solus. Oh, sorry, for the first from Gedrus. What is the meaning of the terms CMD in the context of CPUs? I remember when Intel released SSC, it was so exciting. Single instruction, multiple data. Vilnius is holding strong. Which of these functions are transparently replaced by equivalent CPU instruction? Okay. RLSDP and Vilnius has quite a lead. It's math, it's ones count. And the last question. What is the meaning of FP? Function projection? No? Okay. So we'll see the leaderboard. Valdemaras took the third place at the last question. Sorry, DB. Okay, Valdemaras, Karolis, and Vilnius. Come here. So how it usually works, first place, first choice. You can, this heavy book has many purposes. So you want a multi-tool. I don't know, I won't try to influence you on the pick. But don't be too long. People are waiting. We want to go drink something. Okay. The biggest one. So, Vilnius, congrats. So,
Second biggest.
yeah, congrats. And the last one on foundations of debugging. Congrats. Yeah, applauses for the winners. So thank you all. I really enjoyed every speech. Paulus gave a good and very amusing talk about sLogging. Saulius gave insights on data pipelines, and Giedrius brought this controversial topic, assembler in Go. So let's chat about it in the networking part. But the biggest thank you is for the speakers and also Vinted and Vilnius Tech Leads Group, which hosted us today here. So in order for these events to continue, speakers, we need speakers. So it doesn't matter your level, it doesn't matter your knowledge, just investigate some topic, beginner level, intermediate, expert, like we welcome everyone. And I'll be waiting for your private messages in LinkedIn to make it happen next time. Thank you.